Hello everyone, today we'll be going over Mathematics, May June 2021, paper 5-2. This is probability and statistics first, and we have a time limit of 1 hour and 15 minutes. So let's get started. An ordinary fair die is thrown repeatedly until a 5 is obtained. So our success is obtaining a 5, which means that this is a geometric distribution. And then the number of throws taken is denoted by the random variable x. So x follows the geometric distribution with probability p. And since the event of success is obtaining a 5, and we know that it's a fair die, so obtaining a 5 in a fair die is with the probability of 1 by 6. So the probability p here will also be 1 by 6. That's our parameter. Now we need to write down the mean of x. Since we know that x follows geometric distribution. Alright, I'm just going to write it down. So if x follows geometric distribution with probability p, then the expectation of x, or the mean of x, is going to be 1 by p. And since we know that in our case the probability is going to be 1 by 6, so the mean of x, which is the expectation of x, is going to be 1 by 6, because this is the probability and it can be written as a 6. That's going to be the required mean of x. We need to find the probability that a 5 is first obtained after the 3rd throw but before the 8th throw. Alright, so alright, these are the number of throws. So we require the success. The success is that a 5 is first obtained after the 3rd row. So that's after the 3rd row, but before the 8th row. So that's going to be right here. So we need a 5 within these 4 throws. So that's the 4th throw. This is the 5th throw. This is the 6th one. And that's the 7th one. Alright, in order to receive or obtain a 5 for the first time on the 4th throw, that will require 3 failures and then a success on the 4th one, right? And in order to obtain a 5 on the 5th throw, that's going to be 4 failures and then a success on the 5th throw. Similarly, for the 6th one, that's going to be 5 failures and a success on the 6th throw. For the 7th, that's going to be 6 failures and a success. So we're just going to multiply these probabilities, then add up all 4 possibilities. Alright, so the required probability is going to be 3 failures. So if the probability of success is 1 by 6, then the probability of failure is going to be 1 minus 1 by 6, which will be 5 by 6. Then that's 3 times. So that's going to be 5 by 6 cubed into a success. So that's 1 by 6. Plus 4 failures. So that's going to be 5 by 6 to the power 4 into 1 by 6. Plus 5 failures. So that's 5 by 6 to the power 5 into 1 by 6. And then the 6 failures. So that's 5 by 6 to the power 6 into a success. So that's 1 by 6. Alright, let's do the calculations. I'm going to write the values to 4 decimal places for now. So that's going to be 0.0965 plus 0.0804 plus 0.0670 plus 0.0558. This will give us the total of 0.2997. This can be rounded off as 0.3. Now we need to find the probability that a 5 is first obtained in fewer than 10 throws. So 5 can be obtained on the first one, second one, third, fourth, fifth, sixth, seventh, 8th, and 9th. So these are a lot of calculations. So I'm going to calculate it with another approach. Alright, we need success on all of these 9 throws. But if we were to figure out the probability of failures for all of these 9 throws and then subtract it from the total probability of 1, we would get the probability of successes in these 9 throws. Alright, so now the required probability is going to be the total probability which is equal to 1, right, minus the probability of failure in the first 9 throws. We already know that the total probability is equals to 1 minus, we need to figure out the probability of failure in the first 9 throws. Like I said before, the probability of success is 1 by 6, which means the probability of failure is going to be 5 by 6. But we're failing in all of the 9 throws, so that's going to be 5 by 6 to the power 9. This gives us the probability of 0.806. That's going to be our answer. The weights of bags of sugar are normally distributed. So I'm going to denote X with the weights of bags of sugar. And we're given that these are normally distributed. So X follows a normal distribution with the mean of 1.04 kg and the standard deviation of sigma. So that's going to be sigma square since we denote the variance as our second parameter. And we're also given a random sample of 2000 bags of sugar. So the random sample n is going to be 2000. And in the random sample of 2000 bags of sugar, 72 weighed more than 1.10 kg. So this is just the probability because we have the total number of bags is 2000, and out of these 2000 bags, 72 weighed more than 1.10 kgs. Alright, so that's just going to be X greater than 1.10. That's the probability, 72 out of 2000, so that's going to be 72 divided by 2000. Since we already know that X follows a normal distribution, the first step would be to standardize it. So that's going to be Z is greater than 1.10. So standardizing always requires Z to be equal to X, which follows a normal distribution, minus the mu, which is going to be the mean of the distribution, divided by the sigma, that's the standard deviation. So we need to subtract the mean, that's 1.04, and divided by the standard deviation, which is sigma. Alright, this is equals to 72 by 2000. So that's equivalent to 0.036. Alright, so that's going to be Z is greater than 0.06 divided by sigma. And this is equal to 0.036. Alright, since we've completed the first step of standardizing, so the second step would be to drop the probability distribution. Alright, that's the mean of 0. And we have that with the value of 0.06 divided by sigma, the greater portion has the probability of 0.036. And since we know that the probability to the right side of the mean is 0.5, and since 0.036 is less than this value of 0.5, so this value of 0.06 divided by sigma is somewhere around the tail. So here is 0.06 divided by sigma, and the probability greater than this value, right? So this area is going to be 0.036. Alright, if the greater area is going to be 0.036, then the area lesser than the value of 0.06 divided by sigma would be 1 minus 0.036, which is equivalent to 0.964. So now we're looking for a probability of 0.964 on our normal distribution table, since the table only gives the values lesser than a certain number, right? So that number is going to be 0.06 divided by sigma. So we need to look for the probability value of 0.964. Alright, so we're given 0.9633 with the value 1.79, but we need a value of 0.964. So we have the difference of 0.0007, which means that if 7 is picked on from this side, so that's going to be right here, which is for the column at 8. So the corresponding figure for the probability of 0.964 is going to be 1.798. All right, so now we know that the Z value right here is going to be 1.798, which is equal to 0.06 by sigma. Now let's solve for this simple equation. From the table, 0.06 divided by sigma is equal to 1.798. So that sigma equals to 0.06 divided by 1.798, which means that sigma has a value of 0.0334. That's the required answer. Now, on each day that Alexa goes to work, the probabilities that she travels by bus, by train, and by car are 0.4, 0.35, and 0.25 respectively. And when she travels by bus, the probability that she arrives late is 0.55. When she travels by train, the probability that she arrives late is 0.7. And when she travels by car, the probability that she arrives late is x. Now, on a randomly chosen day when Alexa goes to work, the probability that she does not arrive late is 0.48. All right, I'm going to draw a tree diagram because the question gives a conditional probability and is always easy to visualize the probabilities with the help of a tree diagram. All right, I'm going to denote the bus by B, the train by T, the car by C, and being late for work will be L, and then not late for work will be L bar or L dash, so that's not late. All right, first we have the three possibilities that she travels by, right? So that's a bus, a train, and a car. Now the probability that she takes a bus is 0.4. The probability that she takes a train is 0.35. And then the probability that she takes a car is 0.25. And now further, there are two possibilities when she takes a bus. She can be late or she can be not late. Similar for the train, she can be late or not late. And similar for the car, she can be late or she can be not late. So that's late, not late, let, not let, late, and not let. All right. Now, when she travels by bus, the probability that she arrives late is going to be 0.55. And if the probability of being late is 0.55, then the probability of being not late is going to be 1 minus 0.55, right? That's going to be 0.45. Now for the train, the probability that she arrives late is 0.7. Again, if the probability of arriving late is 0.7, then the probability of not arriving late will be 0.3. Similar for the car, the probability that she arrives late is going to be x. Then the probability that she arrives not late is going to be 1 minus x. All right, and then on a randomly chosen day when Alexa goes to work, the probability that she does not arrive late. So probability of not being late is given as 0.48. Now there are three possibilities. Either she can take the bus and not be late, or she can take the train and not be late, or she can take the car and not be late. So that's the total probability of 0.48. Now, taking the bus and not being late will have the probability of 0.4 multiplied by 0.45. So that's 0.4 into 0.45. Now, the probability of taking a train and not being late, that's going to be 0.35 multiplied by 0.3. Now, the probability that she takes a car and is not late is going to be 0.25 into 1 minus x. So that's 0.25, 1 minus x. This is equal to 0.48. Alright, 0.4 into 0.45, that's going to be 0.18 plus 0.35 into 0.3, that's going to be 0.105 plus, let's open the bracket, so 0.25 into 1, that's going to be 0.25, and then 0.25 into minus x, that's going to be minus 0.25x. That's equal to 0.48. Alright, now 0.18 plus 0.105 plus 0.25 is equal to 0.535 minus 0.25x equals to 0.48. Now if you move the negative 0.25x to the other side, that's going to be 0.535 minus 0.48 equals to 0.25x. Then x is going to be 0.535 minus 0.48 divided by 0.25, which is equal to 0.22. That's the required value of x. Now we need to find the probability that Alexa travels to work by train given that she arrives late. Alright, so she travels to work by train given that she arrives late. So that's going to be probability T intersection L. This means that she travels to work by train and arrives late divided by the total probability of arriving late. So we're going to figure out the denominator value first. So probability of being late, we can just see from the above diagram. So that's going to be 0.4 into 0.55. That's the probability of taking the bus and arriving late. So that's 0.4 into 0.55 plus the second one will be taking the train and arriving late. That's going to be 0.35 into 0.7. Plus we have the third option of traveling by car. So that's traveling by car and being late, which is x, which also has a value of 0.22. So that's going to be 0.25 into 0.22. Alright, 0.4 into 0.55, that's 0.22 plus 0.35 into 0.7, that is 0.245 plus 0.25 into 0.22, which is 0.055. So this gives us the total probability of 0.52. But there's another way to figure out the probability of being late. So we know the law of the total probabilities. So the probability of being late and then the probability of not being late should be equal to 1. And we already have the probability of not being late as 0.48. So that could have been probability of being late equals to 1 minus 0.48, which would give the same value of 0.52. Alright, this is the value for the denominator. Now we need the value for the numerator, which is the probability when Alexa takes the train and she arrives late. So that's just going to be the second one, 0.35 into 0.7, which is equal to the total probability of 0.471. This is the required answer. A Ferris spinner has sides numbered 1, 2, 2, and then another Ferris spinner has sides numbered -2, 0, and 1. Alright, for the first Ferris spinner, the values can be 1, and the probability of the value being 1 is 1 out of 3. So that's going to be 1 by 3. And the probability of the value being 2 is going to be 2 out of 3. Alright, then for the second Ferris spinner, we have the value of -2 with the probability of 1 by 3. And we have the value 0 with probability 1 by 3 and the value 1 with probability 1 by 3. Now each spinner is spun and the number on the side on which a spinner comes to rest is noted. The random variable x is the sum of the numbers for the two spinners. So x is going to be score for the first one plus the score for the second spinner. Alright, in order to drop the probability distribution table for X, I'm going to have to draw up the joint probability distribution table for the two spinners. Alright, so I'm going to denote the first spinner with A and the second spinner with B. Alright, so A is going to be the column and B is going to be the row. Now A can have the possible values of 1 and 2, and B can have the possible values of -2, 0, and 1. Alright, now the probability of A having a score of 1 and B having a score of -2 would just be the multiplication of their respective probabilities, which is 1 by 3 into 1 by 3. So that's 1 by 3 into 1 by 3, which gives a total probability of 1 by 9. And this will have a score of 1 plus -2. So that's going to be a -1. That's the score right here. Now the second score will be 1 plus 0, which is equal to 1. This will also have the probability of the product of their respective probabilities. So that's going to be the probability of getting 0, 1 by 3, and the probability of getting 1, which will again be 1 by 3. So that's 1 by 3 into 1 by 3 with a total probability of 1 by 9. Then for the third one, that's going to be 1 plus 1, which gives a total score of 2. Again, it's the product of the two respective probabilities, which is going to be 1 by 3 into 1 by 3. That's again 1 by 9. Alright, now that's 2 plus -2. So that's a score of 0. And that's going to be the product of their respective probabilities. Then -2 has a probability of 1 by 3. And a +2 has a probability of 2 by 3. So that's going to be 2 by 9. For the second one, that's 2 plus 0, which means that's a score of 2 with the probability 1 by 3 into 2 by 3. That's the total probability of 2 by 9. For the third one, that's a score of 2 plus 1, which is 3. And the probability is again going to be 1 by 3 into 2 by 3, which gives a total probability of 2 by 9. Now let's draw up the probability distribution table for X. So we know that X can take the values -1, 0, +1, +2, and +3. So that's -1, 0, 1, 2, and 3. Now we need to write their respective probabilities. The probability of obtaining a 1 is just here. So that's the probability of 1 by 9. The probability of obtaining a 0 is only here, so that's 2 by 9. Probability of obtaining a 1 is only once right here, so that's the probability 1 by 9. The probability of obtaining a 2 is in two different places, so that's 2 by 9 plus 1 by 9, which gives a total probability of 3 by 9. And we have a score of 3, that's with the corresponding probability 2 by 9. Alright. This is going to be the required probability distribution table for X. Now we need to figure out the values for expectation of X and the variance of X. So we know that the expectation of X is just the summation of X values along with the product to the corresponding probabilities. So that's going to be -1 into 1 by 9 plus 0 into 2 by 9 plus 1 into 1 by 9 plus 2 into 3 by 9 plus 3 into 2 by 9. This gives the total expectation of 4 by 3. Alright, now we need to figure out the variance. Alright, we know the formula for the variance of X is expectation of X square minus expectation of X whole square. So we already have the second part, that's 4 by 3. We need to figure out the first part. So that's going to be expectation of X square. That's just the summation of X values squared into their corresponding probabilities. So that's going to be -1 square into 1 by 9 plus 0 square into 2 by 9 plus 1 square into 1 by 9 plus 2 square into 3 by 9 plus 3 square into 2 by 9. This gives the total expectation of X square of 34 by 9. So let's just substitute these values. So that's going to be 34 by 9 minus 4 by 3 whole square, which gives the value of 16 by 9. That's the required variance. Now, every day Richard takes a flight between Aston and Beijing. On any day, the probability that the flight arrives early is 0.15, the probability that it arrives on time is 0.55, and the probability that it arrives late is 0.3. And we need to figure out the probability that on each of 3 randomly chosen days. So that's the sample. Richard's flight does not arrive late. So not arriving late is going to be our event of success. So I'm going to denote the variable x as the number of days on which the flight does not arrive late. So we're looking at a sample of 3, right? Which means that x follows the binomial distribution with the total number of samples 3, and the probability p is going to be the probability of flight not arriving late. So if it arrives on early, that's not arriving late, and if it arrives on time, that's also not arriving late, right? So that's the sum of 0.15 plus 0.55, which gives the total probability of 0.7. So that's the probability p with the value 0.70. And we need to figure out the probability that on each of 3 randomly chosen days, so x equals to 3. We need to figure out this probability. That's going to be 3c3 into 0.7 cube into q. If the value for p is 0.7, then the value for q is going to be 1 minus p, that's 0.7, which gives the value at 0.3. So that's 0. Then the total probability is going to be 0.343. All right. Now we need to find the probability for 9 randomly chosen days. Richard's flight arrives early at least 3 times. Now I'm going to denote the variable x as the number of days on which the flight arrives early, because we're talking about the flight arriving early. Now we have a sample of 9 days. So x follows a binomial distribution with the total sample n with the value 9, and the probability is going to be that of the flight arriving early, and that's going to be 0.15. Now we need to figure out the probability that the flight arrives early at least 3 times. So it has to arrive early at least 3 times. So it can arrive early for the days greater than 3. So that's greater or equals to 3. Alright, we know that x can take the possible values of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we need to figure out the values where x is greater or equal to 3. So that's going to be 3 to 9. But those are 7 calculations, which is going to be lengthy. So we need to shorten it. And how can we do that? We know that the total probability from 0 to 9 is going to be 1. And if we subtract the probabilities for 0, 1, and 2, we'll get the required probabilities for the days 3 to 9. So that's going to be total probability of 1 minus probability of x equals to 0, 1, or 2. So that's going to be 1 minus probability x equals to 0 minus probability x equals to 1 minus probability x equals to 2. Now we're just going to use the binomial formula. So that's going to be 9c0 into probability is 0.15 to the power 0 into, if the value of p is going to be 0.15, then the value of q is going to be 1 minus 0.15, which is 0.85. So that's going to be 0.85 to the power 9 minus 9c1 into 0.15 to the power 1 into 0.85 to the power 8 minus 9c2 into 0.15 square into 0.85 to the power 7. Alright, that's going to be 1 minus, I'm going to write down till 4 decimal places, so that's 0.2316 minus 0.3679 minus 0.2597, which gives the total probability of 0.1408. And if we're to round off this to 3 decimal places, that's going to be 0.141. Now 60 days are chosen at random. So the sample is now 60 days. We need to use an approximation, which means that we need to transform the binomial distribution to the normal distribution in order to find the probability that Richard's flight arrives early at least 12 times. So if x is an event of the flight arriving early, it follows the binomial distribution. Now the sample is of 60 days, and the probability of flight arriving early is 0.15. In order to approximate a binomial distribution to the normal one, we need to figure out the mean and the variance of the binomial distribution. So the mean is going to be n into p. In this case, that's 60 into 0.15, which is equivalent to 9. And the variance is equal to n into p into q, which in this case will be 60 into 0.15 into 0.85, and that's 7.65. So now we can write x follows the normal distribution, and the first parameter of the normal distribution is the mean, which is the expected value of 9, and the second parameter is going to be that of variance, which has a value of 7.65. Alright, now we need to figure out the probability that Richard's flight arrives early at least 12 times. So that's probability x is greater or equal to 12. But we know that binomial distribution is a discrete distribution, and normal distribution is a continuous one. So before finding out the probability, we need to perform a continuity correction in order to maintain that a normal distribution is a continuous one. So we need to figure out probability that x is greater or equal to 12. So if it's 12 right here, that's 12.5, that's 11.5. And we're looking at values greater, so we're looking this way. And we can see there's an equals to sign as well, which means that we include the 12. So we're going to see or look at the values greater, including the value 12. So that's going to be from 11.5. So we're looking at the values greater than 11.5. Alright, now it's just a simple normal distribution problem, and the first step is to standardize it. So that's going to be z is greater than 11.5 minus the mean value of 9 divided by the standard deviation. So that's going to be root under the variance, that's 7.65. Now this gives the value z is greater than 0.904. Alright, we've completed the first step of standardizing, so the second step will be to drop the probability distribution. So that's the mean of 0, and we need to figure out the probability greater than 0.904. So that's somewhere around here, 0.904. We require this value. But we know that the normal distribution table only gives the value for the lesser one. So in order to do so, we can figure out the probability less than 0.904 and then subtract it from the total probability of 1. So this is going to be equivalent to 1 minus probability of z is less than 0.904. Now we'll look for this probability value in the normal distribution table. So we're looking for the z value of 0.904. So we already have the value for 0.90 right here, but we also require the third decimal place of 4, which is given in this column. So that's going to be a value of 10. Alright, now the required probability is going to be 0.8159 plus 0.0010, which gives the total probability of 0.8169. Now we can just substitute this probability. So this is going to be 1 minus 0.8169, which gives the value of 0.183. That's the required answer. Now we need to figure out the total number of different arrangements of the 8 letters in the word tomorrow. So the total number of letters, I'm going to denote it with n, that's going to be 8. Now the repeated letters. So the first repeated letter is O, which has a frequency, I'm going to denote it with R1 of 3. The second repeated letter is R, and it has a frequency of 2. Now we need to figure out the number of arrangements. We are not given any restrictions here, so this is going to be number of arrangements without any restrictions. So this is always going to be the total number of letters factorial divided by the frequency of the repeated letters factorial. So in this case we have 2, so that's R1 factorial into R2 factorial. So that's going to be 8 factorial divided by 3 factorial into 2 factorial, which gives the total value of 3360. Now for the second one, we need to find the total number of different arrangements of the 8 letters in the word tomorrow that have an R at the beginning and an R at the end, and in which the 3 O's are not together at all. So we have double restrictions here. Alright, we have 8 letters, and we require R at the beginning and an R at the end, which means that we need to find the arrangement for the remaining 6 letters. So we're only considering the remaining 6 letters of T, O, M, O, O, W. And for these 6 letters as well, we only require the arrangement in which the 3 O's are not all together. So whenever we're talking about arrangements with letters not together, it is easier to figure it out by subtracting the number of arrangements in which the letters are all together from the total number of different arrangements without any restrictions. But like I said before, this is a case of double restrictions. So without restrictions is just going to be the arrangement of these 6 letters. So let's just figure out the arrangement of these 6 letters. Here the total number of letters N is going to be 6, and then the repeated letters is only O, which has the frequency of 3. Now the number of arrangement without restrictions, so we're only talking about the 6 letters. So this is going to be n factorial divided by R1 factorial, which is 6 factorial divided by 3 factorial. That gives us a total of 120. Now we need to figure out the arrangement of these 6 letters with all 3 O's together. So if we consider 3 O's to be a single letter, then the remaining letters are going to be T, M, and W. Here the total number of letters is going to be 4, because we consider these 3 O's to be a single letter, and then there are 3 remaining letters, and we do not have any repeated letters. Now the number of arrangements with restriction. And here the restriction is that all 3 O's are together. Alright, this is just going to be n factorial divided by r factorial, so that's 4 factorial divided by 0 factorial. So that's just equal to 4 factorial, which is equal to 24. Now the required number of arrangement is the arrangement of these 8 letters in which R is at the beginning, R is at the end, and the 3 O's are all not together. So that's going to be the difference between the number of arrangements without restrictions and the number of arrangements with restrictions, considering only the 6 letters. So that's 120 minus 24, which gives the total number of required arrangements at 96. Now the 4 letters are selected at random from the 8 letters of the word tomorrow, and we need to find the probability that the selection contains at least one O and at least one R. So we're talking about 4 selections from the total letters of 8, and we have 3 O's and 2 R. So there cannot be more than 2 R and there cannot be more than 3 O's, right? And we're selecting the 4 letters, which means that the remaining letters T, M, and W can also be a part of these 4 selections. Alright, so we require at least one O and one R, so that's going to be one O, one R, and 2 can be other remaining letters. Let's increase the values of O first. So there can be 2 O, 1 R, and 1 other remaining letter, or there can be 3 O, 1 R, right? Now, let's increase the letter of R, so that's going to be 1 O, 2 R, right? Or there can be 2 O's and 2 R. Alright, that's all the possible selections. So we're selecting 1 out of the 3, so that's 3C1. We're selecting 1 out of the 2 R's, so that's going to be 2C1. And we're selecting 2 from the remaining letters. So the remaining letters is going to be 3. So that's 3C2. This gives us the total of 18 selections. For the second one, we're selecting 2 O's from 3, so that's 3C2. We're selecting 1 R from 2 R's, so that's 2C1. And we're selecting 1 letter from the remaining 3 letters, so that's 3C1, which gives us the total selection of 18. For the third one, that's going to be 3 selections of O from 3 letters, so that's 3C3, into 1 selection of R from 2 R's, so that's 2C1. And we're not selecting any from the remaining letters, so that's going to be 3C0, or we can completely ignore this part. This does not change the answer. So this gives us the value of 2. For the fourth one, we're selecting 1 O from the 3, so that's 3C1. We're selecting 2 R's from 2 R's, so that's 2C2. And we're selecting 1 letter from the remaining 3 letters, so that's 3C1. This gives the total possible selection of 9. And for the last one, that's 2 O and 2 R, so 3C2 into 2C2, and we are not selecting any of the letters from the remaining 3, so that's 3C0, or like I said before, we can completely ignore this, and it will not change the answer. So that's going to be 3. Now the total possible selection is going to be the sum of these 5 selections. So that's 18 plus 18 plus 2 plus 9 plus 3, which is equal to 50. And that's going to be our answer. So the heights in centimeter of 11 basketball players in each of 2 clubs, the Amazons and the Giants, are shown below. We need to state an advantage of using a stem and leaf diagram compared to a box and whisker plot to illustrate this information. Alright, we know that the stem and leaf diagram is going to include all of these values, every one of them. But in a box and whisker plot, we're going to only include the smallest value, the first quartile, second quartile, third quartile, and the largest value, right? It does not represent or include all of these data. So the advantage is going to be that the stem and leaf actually includes all data. Now we need to represent the data by drawing a back-to-back stem and leaf diagram with Amazons on the left-hand side of the diagram. Alright, so Amazons are going to be on the left. Let me draw the stem. So we have Amazons on the left-hand side, and we have the Giants on the right-hand side. Since we have a 3-digit number, I'm going to place the first 2 digits on the stem. So let's look for the smallest first 2 digits. So that's 17 for Amazons, and I think that's 17 for Giants as well. Alright, let's look for the highest one. For Amazons, that's going to be 21. For Giants, that's going to be 20. Alright, so the values in the stem is going to range from 17 to 21. Let's just note that down first. So it's going to be 17, 18, 19, 20, and 21. Let's fill up the values for leaves. Let's do for the giants one first. All right, with the stem of 17, we have a value of 5. That's it. So we only have a value of 5. For the Amazons, we have a value of 8. That's the only one. All right, let's look for the stem with the 18 for giants. So that's going to be the values 2, 4, 7, and 9. So that's 2, 4, 7, and 9. Let's look for the stem 18 for Amazons. So that's going to be 1, 2, and 4. Alright, now let's look for the stem of 19 for giants first. So that's going to be 2, 3, 5, 5, and 5. So 2, 3, 5, 5, and another 5. Now we're looking for 19 in Amazons. So that's going to be 8, 0, 6. So in order, that would be 0, 6, and 8. That's 0, 6, and 8. Now let's look for 20. For the giants, that's only going to be 4. Then for Amazons, that's going to be 5, 1, 2. And in order, that would be 1, 2, and 5. Now for 21, we already saw that giants does not have any numbers, but for Amazons, there's one with the value of 5. Alright, we're done with the diagram, but we need to include the key. So I'm going to include this portion. So that's 1, 20, and 4, which means 201 centimeter for Amazons and 204 centimeter for giants. So this completes our stem leaf diagram. Now we need to figure out the interquartile range of the heights of the players in the Amazons. Alright, so we know that the interquartile range is going to be the upper quartile, which is Q3, minus the lower quartile, which is Q1. So we first need to figure out the Q3 and Q1 for the players in Amazon. So we know that we are given the height of 11 players, right? So n is going to be 11. And since this is a discrete data, that's going to be n plus 1 into 3 by 4th item. And n is 11, which means n plus 1 is 12 into 3 by 4th item. Right? So that's going to be the 9th item. Alright, so the 9th item, that's 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th. So 9th item is going to be 202 centimeter. So that's going to be the Q3. Now we need to figure out the first quartile. So that's going to be n plus 1 into 1 by 4th item. So we know that n is 11, which means that n plus 1 will be 12 into 1 by 4th item. So that's going to be the 3rd item, which will be, this is the first one, second one, third one. So that's going to be 182. So now the interquartile range is just going to be 202 minus 182, which is 20 centimeter. So we now have 4 new players joining the Amazons, and the mean height of the 15 players in the Amazons is now 191.2 centimeter. That's the new mean height, and the height of 3 of the new players are 180, 185, and 190 centimeter. Alright, let's just figure out the mean for the previous 11 players. In order to do so, we require the summation of the heights of those 11 players. So let's look at that first. So the summations is going to be 205 plus 198 plus 181 plus 182 plus 190 plus 215 plus 201 plus 178 plus 202 plus 196 plus 184. So the summation is going to be equal to 2132 for the 11 players. Alright, so we know that the mean now for the 15 players is 191.2. And in order to figure out the mean, we just need to sum the height of all of the 15 players. And we already know that the sum of the height of the previous 11 players was 2132 centimeter. And then the 3 new players have the heights of 180 plus 185 plus 190. So we need to figure out the height of the remaining 4th player, right? And that needs to be added in order to figure out the mean. Divided by the total number of players, that's going to be 15. Now this is going to be equal to 191.2. Alright, now 2132 plus 180 plus 185 plus 190 is equal to 2687 plus h divided by 15. That's equal to 191.2. Now this is just a really simple equation. So that's 2687 plus h equals to 191.2 into 15. Now the height of the remaining 4th player is going to be 191.2 into 15 minus 2687. So that gives us the required height at 181 centimeter. So the height of the 4th player is going to be 181 centimeter. That's the required answer. Alright, this brings us to the end of this set. If you found this video useful, make sure you hit the like button, make sure you leave a comment below, and make sure to hit the subscribe button and the bell icon in order to view more of my contents in the future. Thank you.